they say
if it's a big mess, then yeah. All right, so we only have about 20 minutes left. We are being recorded here, and I know that there are several people that are going to be out for different things over the next few days, like baseball games.
That's me.
That's you too?
Yeah.
Man, how many are going to be out for the baseball game?
I just had to be here.
Yeah, sure.
That's good.
I think school is more important.
Baseball
Baseball
is
so boring to watch.
The bonding Hey, take it easy on that thing.
It's fun to watch.
Okay, we're going to cover almost the entire time in this chapter covalent bonding. What goes on with sharing electrons, polar bonds, that kind of thing. But at the beginning here, we should take a look at all three major types of bonding. Spencer, let's go on to the next one. Ionic bonding, covalent bonding, metallic bonding. These are three different ways that atoms are held together in a compound. Actually, not necessarily in a compound because we got the metallic there. Ionic bonding is typically involved when you have a metal bonding to a non-metal. That's not always the case because there are some times where you'll have a metal involved in a covalent bond. That's not very typical, but like there are sometimes, once in a great while, you'll have an organic molecule with a metal on it.
Sure will.
Have you seen it before?
Yeah, RoboCop.
What is possible? What?
RoboCop.
That's true, RoboCop. Yeah, it's a great example. Yep. A fictional example, but yeah. Covalent bonds occur between, generally, nonmetals, and I shouldn't have said plus H, I should have said including H. You don't have to have H in a compound that has covalent bonding in it. It's very common, but it doesn't have to be there.
But we have to start with organic.
I feel like we probably should have done it.
Yeah.
I think this is kind of easy, to be honest.
This is out.
It's a good way to scare away the people who shouldn't take it. AKA almost me.
Hey, I really shouldn't have, but hey.
What? Organic chemistry was easy. I never had that for like the whole entire year.
Quit complaining. We're learning this.
No, why do you do this last though? Doesn't it make more sense to do it first?
No. I mean, would you rather have Orgo now?
I think this is a very easy chapter compared to the others, so I'd rather end easy than finish.
Yeah.
I'd rather end easy than end hard.
So then when it all of a sudden gets hard in the second section, kids are like, oh, I thought AP chemistry was going to be easy. We
Yeah,
talk
then
about
they took-
bonding and dot structure.
I'd rather do the hard stuff first. And also, because there's so much of this on the AP exam, I think it's good to have it fresh in our mind.
Why not
Yeah,
just
well,
do
you
it at the same time?
Never
Do them all at the same time?
Yeah.
That's good. It would take like 3 weeks.
One
and then
huge
the
ass
other-
chapter.
Take one big test.
The other 27 weeks we could just party.
Why don't we do
Well
that?
said. Next year. Thank you for the suggestion. Next year we'll go through this class.
I'll be taking class.
All chapters at the same time at the beginning of the year. Yep. Oh.
One weekend you can just knock out all 13 reviews.
Wait, did anyone
Yeah.
else realize that Drew's actually recording this?
So that quiz is the day after we get back.
Yeah, what the heck?
It's the day that we get back.
I'm gonna have
Why?
to when watching this.
Again, off the
That's messed up.
Life is rough.
one day.
What is this? Have you ever seen that movie?
It's not that much paper to take with you.
Okay.
All right, let's go on. Spencer, let's move. Now, the difference between ionic and covalent is not a very clear, distinct difference. A covalent bond, if it's purely covalent, it has to be a diatomic element. 2 atoms of the same element sharing electrons, like Cl2 or Br2 or H2, where the electrons are not at all being pulled toward one electron or the other, one atom or the other. They're right in between the shared atoms, or the atoms that are shared. Ionic compounds, we think of ionic compounds as when electrons are transferred. The nonmetal takes the electrons, the metal loses the electrons. However, the Zundals, you know that they're purists. And they won't let us think of ionic compounds as purely ionic. There is no such thing. when a metal loses electrons to a nonmetal, that metal still has some stake, some claim to that electron. Even though we make it seem or sound like the nonmetal just totally takes the electron. According to the purists, that's not totally true. And we can measure how much the nonmetal is taking the electron based on the electronegativity. That's why we learned about electronegativity last chapter, is differences in electronegativity. If they're big, that's either a polar or ionic bond. If there's no difference in electronegativity, that's what we have here. That would be a purely covalent bond. So it's kind of a continuum between covalent and ionic bond. Everybody okay?
Yeah.
All right, let's move on. So for ionic compounds, we'll start with those first. Ionic compounds always are solid at room temperature. You can heat them up real hot and get them to melt down, but at room temperature they're solid because they have to arrange themselves in a very orderly configuration. You have the positives and negatives. The positives surround themselves with negatives. The negatives surround themselves with positives in a crystal. A crystal is a very orderly arrangement.
Is that the lattice crystal?
Yeah, that would be the crystal lattice.
Crystal
That's
lattice.
right.
I bet you made that molecule yourself.
In my spare time.
Are we responsible for crystal lattice?
Yes, after today you will be.
Crystal
Yay.
cabbage.
I remember the lattice method.
Lettuce.
Oh my goodness.
Yes. What are they looking at? Wait, what?
The last method where you do like squares and multiplications.
Oh, I
Oh, yeah.
Okay.
Right. And that was arranged very
Yeah,
orderly.
like a crystal.
Yes. Tell me, you've got green particles and I called them blue, and then one of my hours got after me and saying they were purple. Purple. Fine. Green and
Indigo.
purple.
Gosh.
Nah.
Wait, they look.
Oh,
Wait,
the purple ones are positive.
Wait, Spencer, does it look red on your screen?
No, it looks very purple.
Oh.
Wait, doesn't
Who cares?
It kind of have a look of red from here, doesn't it?
Yeah.
Okay,
Anyway, so the green to the purples. Which one, green or purple, is negative?
green.
Purple. Purple. No.
How the heck do you know?
You should be able to guess.
Black.
Confidently.
Oh, it's the
What,
smaller one.
LaFont? You're saying green is
You were right.
negative.
Say it again. Say,
They're
Why?
big. They're big.
Because they have
When
extra
atoms-
electrons.
Say it for the camera.
Do it for the man.
When atoms become negatively charged, what happens to the size?
Bigger.
Oh, much bigger. When atoms become positive, they get a lot smaller. So I'm going to guess, with confidence, that the greens are the negatives and the purples are the positives.
Of course you would
You
do
with
with
me?
confidence. You're teaching us this.
Are you right?
All right then.
We are 95% confident.
What though if
You're not doing
it's
stats right
francium fluoride, FRF?
wait. Oh. Ooh.
Francium is the big boy, right? This big, huge atom. If it loses an electron, how much smaller can it get?
Not
It's got 7 energy levels of electrons. It's not going to get much smaller. Fluorine, oh, it's this tiny, minuscule thing. Yes, it's going to get bigger when it gains an electron, but it can't be as big as francium.
Wait.
So if this is francium fluoride, then it's probably the opposite. The francium is going to be the big boy. Yeah?
Wait, but if it's francium, if it loses an electron, it goes to like a normal gas, doesn't it?
Yeah, sure it would, but it's not going to get a whole lot smaller. Just a little bit smaller. Because francium has so many levels of energy.
So we can assume that Rn is a pretty big noble gas.
Yes. Yes, we will. Yep.
Because atomic radius.
Because of all that shielding that happens, all the electrons that are inside the outer energy. Yep. So anyway, now are you comfortable when I say there's no definite molecules? Does that seem like you can buy that. Now, the reason for that is, let's take a look. This negative ion, which positive ion does it belong to?
Who knows?
You don't know, do you? Because of this crystal arrangement, this negative ion belongs to all the crystals around it. In a water molecule, it bends, if you can remember that.
Ooh, yeah.
It's got the 2 lone pairs. Now the water molecule, this whole unit is a standalone unit. This oxygen is chemically bonded to that hydrogen and to that hydrogen, and it's not chemically bonded to any other hydrogens. No? So that's a big difference. Covalent bonding, you're going to get distinct molecules that represent that compound. With ionic bonding, you get this network. And all the negatives are surrounded by positives, all the positives are surrounded by negatives. And the negatives try not to get too close to each other. The positives try not to get too close to each other because they repel, they push away from each other. So you get this big network in an ionic compound. Unlike in a covalently molecular compound, you've got distinct molecules. Spencer? Let's go on, and we're going to just take on this last slide. Here it is. The one thing that you were so curious about, now I can scratch that itch for you.
Lattice.
All right.
Lattice.
The lattice energy. Do you know what a lattice is in your garden?
Lettuce.
Yeah.
Oh, it's the
Not
wooden,
lettuce.
not the wooden thing that you use to.
The wooden
salad.
Yeah, you used to.
Green stuff.
Right? Where vines can grow on them. You saw the picture, the model of the ionic compound on the last slide. It's very organized where you've got the negatives and positives all very specifically arranged. The lattice energy is the energy involved when ions join together to make a solid. Bonds are forming. Yeah.
Yes.
When an ionic bond is made, what happens with energy when bonds form? Always.
Energy is given off.
Energy is released. So lattice energy is always going to be, and that's why I chose carefully this word. I didn't say the energy changed. It's always released when it's ionic solid is made.
Lettuce.
So this equation represents the lattice energy. This also represents a law in chemistry called Coulomb's law. There's a name that you recognize, Coulomb.
Coulomb.
Who is a person?
Yeah.
Yeah, this is a K. K times Q1, Q2 over R. And the variables are defined on it. The K value you're not going to have to worry about. Just know that it's called Coulomb's constant.
Cool. That doesn't
No,
sound cute.
and it's not the rate thing either. It's just a different K. Not that one either.
It's a tie. Will it give it to you?
Sick, dude. The race.
It's based on the atomic radii, or the ionic radii. Because these are
When
ions.
did you get that?
You have to be given them on a table. Yep. Or you just have to know the trends. Who has big radii and who has small radii? That kind of thing. In fact, we're going to do that. Brooke?
This isn't something we see on the multiple choice because there's no math.
Oh yes. You saw it on multiple choice in the studying. There were questions about lattice energy.
Yeah, but it's not gonna be like that.
We didn't know which was the right answer.
Right. You just have to understand that lattice energy is affected by the charges of the ions and by how big they are.
Wait, this is so big. Wait, oh. Just edit that.
You tried to.
Yeah. Wait, you didn't even, you have. I love Mr. Dan. Like, wait, why is that
I love this kid.
I love people talking about
Let's not, please.
I like
when you started electricity at the end.
So the charge is gonna cancel out change in radius? Is that what that like? Or like the radius won't matter?
For which one?
The last slide.
This one right here?
Yeah.
When you have differences in charge and radius, and you're trying to figure out who has a bigger lattice energy, charge is more meaningful than radius.
Okay.
That's what I mean by Trump.
Wait, what is it?
What is the sign on lattice energy always going to be? This delta H is always going to be positive or negative?
negative.
And why?
Because we're releasing energy.
Oh wait.
Yes, you're always releasing energy, but mathematically why when you look over here?
because K is always negative.
I didn't say so, you